Yeah, thank you, Dirk-Uwe, for the kind introduction. So, yeah, a warm welcome from my side. Also, good morning. So today I would like to talk about intelligent operating methods and their influence on components for hybrid marine propulsion systems. So I will actually like to start to cover some media echo around this topic. So, for example, that companies are talking about the challenges in the shipping industry that persist, or even that the sustainability of cruise ships, for example, is questioned actually here by this BBC article, or even the European Environment Agency is stating that the EU maritime transport sector has made progress, but still faces major challenges in reducing emissions. So there's actually a lot of action we need to do in the coming years. So we can ask ourselves, where is the direction of the maritime industry? So how is it actually facing these challenges? So I would like to start with the agenda. So I will start with an introduction and motivation. Then we will look into hybrid propulsion concepts. And then I would like to elaborate a bit on energy management methods. Then we will look into hardware implementation and the validation. And finally, looking into another method where we also used environmental data. So yeah, let's start with the introduction and motivation. So here we have a little roadmap or waterway, maybe we can say. So in the beginning, we can state that the shipping right now produces 4% of the EU global greenhouse gas emissions. So in total, you can see this split actually on the graph as well. So it's actually second to road transport, and this really shows us where the big problem is. So there are some short-term measures that we can implement, for example, using low-emission fuels, for example, LNG or methanol. But there are also market-based measures, for example, CO2 tax. Then we also have CO2 reduction goals. So, for example, minus 40% until 2030. But we also have medium-term measures until the year 2050. So here we are talking about zero emission fuels, for example, hydrogen in fuel cells. And the reduction target here from the IMO is minus 70%. And also we're looking into long-term measures. So that's beyond the year 2050. So we are here talking about a greater integration of renewable energies, for example, that you produce a green hydrogen on site and then either use it as cargo on ships or to fuel them. And as a perspective, we're looking into sustainable shipping in the year 2100. At least that's the plan that the EMO is right now implementing. So maybe the frames around my work is a research project. So the research project was called Nautilus. It was funded by the European Union, and its goal was the development of a hybrid propulsion system consisting of batteries and fuel cells. So here's actually a 3D rendering of a potential ship. This might not be a technically feasible solution, but it's just illustrate like how much of the volume could possibly be taken by the components. So here on the left side, we can see a fuel cell component, and on the right side, a battery rack. And on the top, also some tanks for the fuel that we're using. So now I would like to state some relevant questions which we would like to elaborate on. So the first one would be, how can we actually use authentic power demand profiles in order to determine an efficient sizing of this hybrid propulsion system? The second one would be, how do intelligent energy management algorithms using environmental data compare to conventional ones? The third one would actually be how we can use machine learning techniques in energy management algorithms to increase the efficiency. And the last question is, how effective can we actually test this on a test bench? So here we have set up a hardware in the loop test bench in order to validate the functionality of the algorithms. So let's now take a look at the hybrid propulsion concept. So here I would like to, first of all, show you a little structure or taxonomy where we see different structures of the propulsion train. So these can be subdivided into combustion-based ones, hybrid ones, or electric ones. So if we talk about the internal combustion engine-based ones, so here we can use different fuel types to increase the efficiency. So This could be, for example, using methane or LNG. Furthermore, in a hybrid propulsion system, there could be the combination of a combustion engine plus battery-powered drivetrain. So this could be a retrofit option. So now we're talking about ICE plus battery-powered ones. So this could be a retrofit option. Where possibly this would enable an emission-free harbor cruise, for example, that you would turn off the engines when entering or leaving the harbors. Then we're looking into battery plus fuel cell powered drivetrains. So these are also actually potentially emission-free depending on the utilized fuel type. So for example, if we're talking about hydrogen, this would be locally emission-free. If the fuel cell, of course, uses other means of fuel, this would be different, but it's at least an interesting solution as well. So the electric drivetrain, here we're talking about battery-powered ones. So these are emission-free, but limited due to the energy density of lithium-ion batteries. So we will look into that in a minute. And then finally, we have the fuel cell-powered one. So these are potentially emission-free, but they might be limited in their dynamic capabilities depending on the technology, and we will look into that in a minute as well. So I would like to highlight these three drivetrains actually here. So the ICE one, the battery plus fuel cell powered, and the battery powered one. Yeah, let's first take a look at a conventional drivetrain. So it's composed of an internal combustion engine. So here we're actually not limited in ship size. So most ships that are driving these days actually work with an internal combustion engine, obviously. So here we have different fuel options, and you can already see that the energy densities of these fuels is quite high. So that's why they're also so prominent. Moreover, we also have economic incentives here because the fuels are typically very cheap. So the applications here is for all vessel types, basically. Then let's take a look at the battery electric propulsion systems. So we have already mentioned that they're limited in range. Yeah, this is due to the energy density of lithium-ion batteries. That's right now at around 200 watt-hours per kilogram, depending on the cell type and technology, obviously. This can go a little bit further, but I think we have reached more or less a saturation level, so it won't go beyond, for example, 400. So in comparison, if we're talking about a diesel plus ICE engine once, that actually has an energy density that's more than 10 times higher. So you can see already that's a tough competition here. So applications could be ferries in regions with onshore grid connections, for example, for charging. This already happens in, for example, Scandinavian countries. They have some ferries which go back and forth between fjords, for example, to carry a few passengers. But as said, these are very limited in range. Yeah, let's now dive into the hybrid propulsion systems as a promising solution. So here we are actually not really limited in ship size. Still, the energy density of lithium-ion batteries remain. However, we can also use the energy density of the utilized fuel that the fuel cell, for example, is actually fueled with. And yeah, and here we also have some more fuels actually. So hydrogen, for example, LNG, ammonia could be used, and methanol, just to name a few. Yeah, applications could be, if it's an ICE hybrid, we have already said it could be a retrofit option. If it's a battery fuel cell hybrid, so this is actually a very promising solution for the future, which could fulfill the emission targets. And on the bottom, you can also see like how the power should be distributed between the propulsion components. Yeah, let's now take a look at lithium-ion batteries for maritime applications. So lithium-ion batteries are omnipresent right now and power many transport applications. So we're talking about battery electric vehicles, electric trains, heavy-duty vehicles, and also marine applications, at least some right now. The working principle, I don't have to tell it to most of you, but involves lithium ions moving back and forth between anode and cathode. So I've also plotted the volumetric energy and power density in this Ragone type plot. So you can already see that the lithium-ion battery is actually pretty high here in comparison to most technologies. The gravimetric energy density is between 150 and 350 watt-hours per kilogram. And we have different cell chemistries, which also have different properties. The most prominent one would be the nickel manganese cobalt, so NMC, as we call it. And for commercial shipping, however, a high volumetric energy density is essential, of course, because it increases a ship's commercial viability. Because if you think about a cargo ship or a cruise ship, you want to carry a lot of passengers, a lot of cargo, and so on. So this is a really important issue. So we can say, for example, we can roughly say that you need like a volumetric energy density that is above this or in this yellow shaded region. So one example here would be the MS Roald Amundsen. So that's the ice battery hybrid vessel with a 1.2 megawatt hour battery on board. So this is actually a cruise ship also. So that's also close to the application that we are looking into today. Yeah, let's take a look at the lithium-ion battery cell unpack that we have used in this project. So we're talking about an NMC cell with 64 amp hours. This is the module that we're looking at. So it contains 28 cells. And then finally, on pack level, we're talking about a 40 kilowatt hour battery system that is marine grade. So it's actually from the largest, let's say, marine battery provider, Corvus Energy. Yeah, so how did we simulate the cell actually? So we have used the IZEA frame. So here in this case, we have used a 2RC model. So in combination with pulse excitations that you can see here in the middle, we have obtained the parameters in order to simulate the cell's behavior. And an easy approach here to simulate also on pack level is to just scale it up by the number of cells connected in series. So let's now take a look at solid oxide fuel cells. So they're abbreviated as SOFCs. So fuel cells in general are energy conversion systems that convert chemical energy of a fuel into electrical energy. So there's also different types of fuel cells, similar to the batteries, different technologies. So we have, for example, one very prominent technology is the PEM fuel cell, the proton exchange membrane fuel cell, but also the SOFC is interesting for its properties. So we have a solid ceramic material as an electrolyte. So yeah, so and the working principle is actually shown here on the bottom left part. So you fuel in here on the top left of this plot with your fuel, and yeah, on the right side you actually have your oxidant. In this case, it's oxygen, and then the yeah, electrical energy is generated. So we have a high temperature operation, so it operates between 600 and 1000 degrees Celsius. So that actually enables internal reforming. So if you were to use, for example, methane, you would actually split the molecule and yeah, once again have the chemical reaction that we have seen here. So this increases the efficiency of the fuel cell, and we're talking about efficiencies beyond 60%. It's fuel flexible, so you can use different types of fuels. So that makes it also very interesting for different applications. And it can also be used as a combined heat power plant. So it actually produces excess heat, and which can also increase the overall efficiency. So this is the reason why it's also quite interesting for a maritime sector. Moreover, it can also be used in reverse operation to produce hydrogen. Then it's an electrolyzer cell. So instead of SOFC, it's then called SOEC, solid oxide electrolyzer cell. So this might also be an interesting application for ships, for example, when it's in harbor, that it produces hydrogen while the ship is not moving. So this is the efficiency map of our investigated SOFC system with respect to the output power. So the peak efficiency is at around 66%. The SOFC actually also has a minimum power output threshold, below which the operation is very inefficient due to the auxiliary consumers. So let's now take a look at the component packaging. So a short disclaimer here that this is actually a prototype. So the figures that you will see now are actually yeah, not maybe comparable to commercial products, so be aware of that fact. So it's a 32 kilowatt fuel cell. It operates between 680 and 800 degrees Celsius. And we are talking about 4 stacks which are connected in parallel inside with 8 kilowatts each. So this is actually a 3D rendering, which was also a result of our project, how like this integration could look on a ship on a more containerized solution. Actually, we're seeing here the SOFC stacks here plus the battery pack. Maybe this will be realized differently on ships eventually, but it's also for illustrative purposes, at least how you could connect these this fuel cell. It also has a bunch of other components around it. These are all called balance of plants. Yeah, let's now take a look maybe at some characteristics of the SOFC. So looking into aging aspects. So premature aging of SOFC systems is accelerated by thermal cycling. Yeah. So we're talking about material stress here, for example, delamination or cracks that could occur. And tests that we have conducted at the lab showed a link between a high power gradient and the thermal cycles. So you can see this in this yellow area, for example, when we look at the orange plot. So the orange line suggests that we are ramping up and down the power, and the temperatures then also increased, which leads to a thermal cycle. So we want to avoid a lot of these events. So let's now move over to the application. So looking into the cruise ship, we are actually looking at the Aida Perla. It's a very, let's say, prominent example at this case. So we had extensive data also within the project from the ship. So it has a maximum power of 46.8 megawatts. So you can already see the dimensions are quite big with these kind of vessels. And the maximum speed is around 40 kilometers an hour. That's typically not the travel speed, so that would be around 20 to 30 kilometers an hour. Yeah, the ship looks like this. Its length is 300 meters. And just to compare it to one of the largest cruise ships, I think this is the second largest cruise ship that I'm showing. Right now, it's 62 meters longer. So we're already talking about the larger class of cruise ships here. Moreover, the data that we have used was from one particular year where you can see this on the top right, where the cruise ship was actually moving from Europe, North Sea, then to the Caribbean and then back. So we will also look into the data later in this presentation. Yeah, let's now take a look at the load demand profiles. So this is the power demand of an exemplary day, or actually it's 2 days. So here we are talking about the phases at sea that I've just highlighted in yellow here. So these are characterized by dynamic power demand, which is also possible. So we are ramping up and down depending on the scenario. And this might actually exceed the dynamic capabilities of the SOFC, as we've just learned. That is something which we should avoid. We have actually looked at the different ramps we have seen. So you can see on the bottom 2 plots with a positive rate of change, the maximum, and the negative rate of change. So when we look at the ramp up, which is actually lower in absolute terms, we're talking about circa 1 megawatt per minute ramp. And if we think about this, the SOFC can at maximum change its power output at 2%. So this is also an important figure. We would come up with an SOFC size of 50 megawatts. So you already see when you would put 50 megawatts on this chart on the top, you would probably overdimension your system a bit too much. So that's why also the battery is highly beneficial also not to overdimension. Then if we look at phases at harbor, we can see they're characterized by a steady power supply of circa 6 to 8 megawatts for this cruise ship. We have no propulsion power, obviously, and this is the hotel load plus the auxiliary consumers. Yeah, let's now take a look at the methodology to determine an efficient sizing. So at first, we are actually putting in the SOFC size. So this is something that the user puts in And then we're looking at a load profile analysis, which was conducted. So we're looking into maximum ramps, ramp up, ramp down phases to determine the maximum power that you need. And also we're looking at phases beyond the output limits of the fuel cell. So these then determine the maximum amount of energy. And from these values, you can then determine the size of the battery. And this is then also verified by a simulation. So this is one exemplary sizing of the cruise ship. So we're talking about 35.6 megawatts here for this AIDA Perla concept. And in combination, we have a 17.2 megawatt hour battery. So if we translate this into the racks that we have seen, we are talking about 435 of these batteries in total. Yeah, let's now take a look at energy management methods. So as more or less the heart of the power distribution then. This is a taxonomy of examined energy management methods, and we can subdivide them into 3 groups. So we have the rule-based ones, we have optimization-based ones, and we have learning-based ones. And I want to highlight 2 of them. So this is a simple rule-based strategy based on conditional statements and reinforcement learning algorithms as well from the learning-based section. So yeah, let's look again into this single line diagram. So an energy management method enables an efficient operation, ideally, of the hybrid marine propulsion system. So its primary objective in the case of a battery and fuel cell is the optimal control between these components. And we also can include an error here. And obviously, one of the objectives is also to keep the error small so that there is no deviation between the power demand and the provided power. Ideally, we would also like to exploit efficient operating points for, at least for the primary propulsion means, for example, for the SOFC to increase the resource efficiency. And we have to do this by considering physical and system limitations. So for example, this could be the battery size, the maximum power output, and so on. And a simple rule-based method is actually built on conditional statements, and we will look into that now. Yeah, the rule-based strategies. First of all, some properties around it. So we're talking about conditional statements. So if-else statements, if you were to translate this into code, they're deterministic. So that means that, that there is no random behavior actually allowed. They're easy to implement, and thus this comes with a low computational effort. And we have a robust performance typically for these algorithms, since they're deterministic. Typical implementation for this is an SOC-controlled approach if you have a battery on board. So you are constantly checking your SOC, and according to that, you will set the power of the SOFC, which is then subtracted from the power demand to obtain the battery power. So this is one very simple approach. And moreover, to avoid a lot of switching between the modes, the output modes, we can also implement a hysteresis control to avoid these fluctuations. Yeah, because if you move from mode 1 to 3 here, for example, in this case, we are more likely to reduce the power output of the SOFC, meaning then that the battery could change its operational mode and then always move back and forth between charge and discharge. So we want to avoid this by increasing the interval between these thresholds. So yeah, let's now take a look at the energy management using machine learning techniques. So machine learning is basically actions that an agent should do in an unknown environment to yield a high reward. So rewards can be high efficiency, low fuel consumption, or low stress factors for components, but you can also have different ones. This is very individual and application specific. So on the right side here, you can see this agent environment interaction, which is shown, where the rewards and states are updated and then processed by the agent to determine an action. Yeah, let's now take a look at reinforcement Q learning. It's a specific branch of machine learning. So we are talking about Q or quality values that are rewards that are iteratively improved in order to obtain the best action state space. So we have a few advantages and disadvantages, of course. So We can store this action state space offline, so it can actually act similar to a rule-based strategy once again. It can be a model-free approach, so it means that your model is actually a black box, at least for the algorithm, and we can implement a multi-objective optimization, so that means that you can combine different rewards. So disadvantages would be that it requires a lot of training and a priori knowledge of your application, the simulation, etc. It cannot be used purely online, like, for example, model predictive control. And it's also sensitive, depending on the technique, of course, towards hyperparameter tuning. So it could be that if you change a parameter slightly, that yeah, it messes up your simulation and results. So let's now take a look at the way we have implemented actually the rewards. So we have implemented 4 rewards that you're seeing here on the left side. So the first one is to reward an efficient operation of the SOFC. So we have somewhat basically fitted the parabolic curve of the SOFC. And then the second one would be to penalize dynamic behavior of the SOFC. The third one is to reward operation at a medium SOC. So you can see this actually by this large plateau around 50%. So this is the desired region where you want to operate your battery. And the last one actually penalizes the high power output of the battery. So if it goes above in absolute terms of the maximum power, you automatically reduce your reward. So then you combine this reward then together into something which looks like this. And you do your and then the training iterations are conducted to yield the final results. So if here, for example, this was the result which had the best outcome. So after 300 episodes, we were close to 0, which is in our case the optimum. Let's now take a look at the simulation at first. So we were able to improve our efficiency with this machine learning algorithm. So we have a more frequent selection of efficient operating points, and you can see this on the right side. So once again, we are comparing a very simple conventional strategy to the machine learning one, and we were able to push the efficiency up a bit by selecting more efficient points. Yeah, let's now take a look at the hardware implementation and the validation part. So yeah, this is actually the test bench where we performed our algorithms. So it's located in Stuttgart at the German Aerospace Center, or DLR. So in the middle, we can see our 32 kilowatt SOFC system. It's a bit hidden behind this insulation material. In the background, you see the 40 kilowatt hour lithium-ion battery system. So yeah, and the heart of the controls is actually implemented in this micro lab box, where we have a simulation model flashed on to perform the power distribution. For communication, we have used Modbus TCP and TCP to communicate between the components. Yeah, let's now take a look at the results of the hardware in the loop testing. So here you see 2 plots. I would like to start with the left one for the rule-based strategy. So in the yellow phase, you can see that the P demand is handled by the battery, and that the ramp up is also handled due to a sufficient SOC that we start with. Then we see that a medium power demand actually prevents a higher discharge of the battery system. Then we can see an interesting phase actually highlighted here in blue. So we see a steep ramp down, which is actually one of the critical phases of the SOFC, where the battery needs to be charged in order to compensate. And we can see now here that the battery is charged slightly above the limits that we have set. So this is somewhat critical. And then the ramp down phase is over, and the high state of charge of the battery leads actually to a discharge again to level out and remain a normal operation. So yeah, for the reinforcement learning one, the power output of power distribution is very different. So we see that the SOFC is kept in an efficient operating range during longer periods actually. Moreover, the maximum power output is lower than the one of the rule-based strategy on the left side. So this is also beneficial in terms of stress factors for the battery. And we also have a significantly lower SOC window, which could also be beneficial in terms of calendar aging if we're looking at very high SOCs. Moreover, the fuel consumption overall is slightly lower. Yeah, we now want to put these results also in perspective to, let's say, a scale up. So at first, these are the results from the hill testing. So as mentioned, the fuel consumption was lower. So we have a fuel savings here at around 10%, which is already pretty promising. So and then we did a simulation once again. So these are not obviously not hardware test results or anything. So we just did a simulation of a ship for one entire year to actually also obtain the fuel costs with also the machine learning in comparison. So here we were able to reduce the cost significantly. As an assumption, we have used a hydrogen price of 9.50 euros. So we were able to also reduce the fuel costs by circa 10%. This translates into almost 18 million euros. So that's a quite good business case, I would say, by just implementing different algorithms. Yeah, let's now take a look at the last method. So here we are using environmental data as well. So basically our idea was to use geodata, so position data and weather data to forecast upcoming power demands and adjust the SOFC power preventively, I would say. It's a combination of a real-world cruise profile that we have seen a bit earlier, the geodata, and also historic weather data that we have actually obtained from different sources here. So yeah, for example, one of the sources was the Federal Maritime and Hydrographic Agency of Germany. We have then actually had some episodes, which you can see on the bottom left, where we had gapless data. So there were no data gaps, so we could just purely use these for our algorithms. So we have grouped them according to the trajectory of the cruise. And moreover, you can see the different data sources here in the middle plot. What we also did was to introduce a dynamic rate of the SOFC operation. So this was actually a variable which we tried to minimize with our algorithm. So that means that if this value is lower, it's more beneficial for the SOFC because it was operated less dynamically. So let's now take a look into simulation aspects. So we have we want to obtain now a hydrodynamic relationship between ship speed and the power demand actually. So a formula can look like this. So we have the power demand of the vessel here on the left side. We have a cubic coefficient, and then we have the speed through water, which can be derived by the speed over ground minus the speed of the current. And here we have, for example, used our data that we have obtained also, which was partly historic data. So considering the efficiencies of the drivetrain and the mass of the vehicle, we were actually able to fit the propulsion power to the velocity. So this then obtained our unknown parameters in our simulation. And we were then able to forecast the power demand. And the deviation was actually quite low, as you can see on the very right. So we were able to predict with a certainty of, yeah, or we had at least a deviation of 2.6% here. So the error was quite low. So this we also incorporated into our energy management method. Yeah, this is the power split which we have obtained. And very interesting would be actually for us to take a look now at the dynamic rate of the SOFC. So the dynamic rates for all episodes that you had seen earlier was actually lower with our proposed algorithm. So that means that we are reducing actually the stress factors for the SOFC, and yeah, which can be stated as a good result then for this energy management method. Yeah, let's now move over to the conclusion and outlook. So we had asked ourselves how authentic power demand profiles can actually be utilized to determine efficient sizing. And we had seen that, for example, we analyzed the authentic load profiles. We then also verified this with a simulation environment. Then next, we asked ourselves how intelligent energy management algorithms using environmental data compared to conventional methods. It's the results that you had seen just a few slides back. So here we also were able to basically have a physical relationship between the speed and the power, and then obtain a good prediction in order to incorporate this into an energy management method successfully. And then we had looked at machine learning techniques and how we can also increase the efficiency of the hybrid propulsion system here. Also, again, one of the highlights here that we were able to improve the reward and also improve the efficiency of the propulsion system. And then eventually we wanted to take a look at the validation, the hardware in the loop testing. And here we had seen that we were able to reduce the fuel consumption by almost 10%, which is a quite promising result here for also future studies as well. So yeah, maybe as an outlook, apart from a further improvement of the algorithms that we're seeing, and yeah, also like diving more deep into the different types of techniques, we actually have a very hands-on approach right now. So right now, actually a demonstrator of our propulsion system is running at DLR site in Stuttgart. So it's very different from the hardware in the loop setup that we have seen. So here on the right side, we see the battery container. It actually includes our controls that we have just seen with the micro lab box and the battery. And here in the back, we have the SFC demonstrator. Once again, this is very different. It's more like a commercial solution. It also has a different power output of 60 kilowatts. And also we have a very sophisticated emission analysis here on the left side. So this is quite promising. And of course, we hope to also contribute with this research to a fast, let's say, implementation of these kind of aspects. So hopefully we will see this also on waterways someday soon. Yeah, and with that being said, I would like to thank you for your attention, and I would be happy to engage now in a discussion with you.